Hi everyone, my name is Kanpinyo. First of all, I would like to thank the organizer for having me here and thanks all of you for your interest in my talk. Today, I would like to present you about my latest progress on the idea of twisted cube, which is about how to geometrically realize the twisted cube so we can visualize them similarly to the other geometric shape. In this talk, we will first recall the motivation, the intuition, and the graph-theoretic representation of twisted cubes. Next, we explore the notion of partially ordered space and a special method to construct some of them. Finally, we use this method to define the partially ordered space for twisted cubes and show that they are compatible with the graph-theoretic representation counterpart. Before we start talking about twisted cubes, we need to recall directed type theory and cubical type theory beforehand. Directed type theory gained many attention from the hot community. It is basically just a homotopy type theory, but some part might not be invertible. This is important since it allows us to reinterpret types from infinity group points to be infinity categories. Cubical type theory is the first interpretation of Hot that regained canonicity property. Moreover, it introduced a new perspective to reason about equalities. Cubical sets usually come equipped with the canfiling condition, which is important because it gives us a way to define the composition. However, it is also a source of invertibility. To show this, given any path P from X to Y, we can find its inverse by putting P itself on the left and use identity on the bottom and on the right. Then the inverse of P is awaiting us on the top. The idea of twisted cube originated from an ambition to remove the invertibility from cubical type theory, but restrain other features of it so we can transfer such the feature to directed type theory. Removing invertibilities requires us to directly modify the combinatorial structure of cubes, which from now on will be called standard cube. Our approach to modify the standard cube is to reverse the arrow on the left. Whoa, wait a sec. Isn't this too ad hoc? Not at all. It can even be generalized naturally. To see this, let's see how the standard cubes are constructed. Assume that if we have an n-dimensional cube, we can construct an n+1 cube by duplicate n-dimensional cubes into two copies and prefix everything on the first and second copy with 0 and 1 respectively. Then we group block of cube component-wise. Now, for the twisted cubes, we also do the same thing as the standard cube, but we also reverse everything at the first copy. As a sanity check, you can see that all of faces in twisted n+1 cube are indeed twisted n cube. Everything that I have been speaking so far is just an idea. So let's make it precise by embedding them into graph. For standard cube, we define a function that takes a graph and returns another graph called standard prism. Standard prism will duplicate the input graph and link each of the corresponding nodes together. Then define the standard n-cube graph, which is a singleton irreflexive graph that has been applied by standard prism n times. For twisted cubes, doing everything exactly the same way as standard cube, but we reverse all of the edge in the first copy in the prism. This process is now called twisted prism, and it will generate a twisted cube graph. Although they are not the same combinatorically, twisted cubes should have the same topological space as standard cubes. This is because the only modification is the direction of some part. This suggests that the idea of topological space is not impressive enough to geometrically realize twisted cubes. Therefore, we need some additional structure to capture the sense of direction. To achieve this, we upgrade our geometrical idea from a topological space to a partially ordered space, or Pospace for short, by equipping a closed partial order to the original topological space. We also upgrade the idea of continuous function to a die-map, which is the original continuous function with a condition that it preserves the partial order. An important example of postspace are the Euclidean postspace, which are Euclidean space with product order. Instead of manually comparing any 2 points to define a partial order of each postspace, we will assign a real number for each point on the topological space, which is the same thing as defining a function from the set of points to the set of real number. Then, we use the total order of real number to generate a partial order associated with the original topological space. Please note that we can't use the total order of real number as is. This is because there may be 2 distinct points that have the same number, which violate the entry symmetry of partial order. To fix this, we narrow the scope of possible space down to metric space and require that the different value of 2 points must be at least the distance between them. We also further require that the real value function to be continuous. This will ensure that the partial order is now closed under the topology. For pedagogical and comparison purposes, we will also define the postspace of standard n cubed by the construction in the previous slide, where the underlying topological space is the product of the closed interval from 0 to 1, and the real value function is just the sum of value in every dimension. Now, we are ready to define the postspace of twisted n cubed, where we first define the underlying topological space to be the product space of closed interval from -1 to 1. This is the result of dimension-wise linear transformation 2 times xi minus 1. The reason of stretching the first endpoint from 0 to -1 is to exploit the sign of each value for direction. So reversing a direction is as easy as multiplying a negative number. Then we define the real value function to be a modification of standard cube counterpart. Here, the formula still consisting of n terms containing xi. However, we multiply all of earlier xj to xi because the sign of dimension I will depend on the sign of each earlier dimension j. We also multiply 2 to the power of n minus 1 minus I to ensure that the sum of later term will not outweigh the current term. If the real value function in the previous slide doesn't make sense for you, don't worry. We have a diagram to illustrate the 1, 2, and 3-dimensional cubes respectively. The first column is the navigator. The second column shows the graph-theoretic representation. The third column shows the underlying topological space, and finally, the fourth column shows the assigned value for each extreme point, together with the arrow in the direction that the value increases. The most important message of the diagram here is the comparison between the second and fourth column, where the direction of each edge on the graph precisely matches the direction of the corresponding arrow. This suggests that the real value function of twisted cube actually compatible with the graph-theoretic representation. This compatibility can be made precisely by encoding each graph of twisted cube to a postspace. Then we define a die-map to the corresponding postspace such that the underlying function of the die-map is injective and contains every extreme point of the postspace in its image. As the main result, I have proven that such the die-map exists for every dimension n. This is true not only for twisted cube, but also for standard cube. Unfortunately, I don't have time to go through all the proof. Nevertheless, if anyone would like to see the proof, I'm more than happy to have a further discussion afterward. My presentation ends here. Thank you again for your interest on my talk. And now it's time for question and answer.